All right, welcome to class, everyone. Today, we're going to unpack a piece of technology that we literally all use every single day, yet we rarely ever think about it. The standard household alkaline battery. I mean, you probably have dozens of them scattered around your home right now, just silently waiting to do their job. But how exactly do they work? What's actually going on inside that little metal cylinder? Okay, let's dive into this and explore the absolutely fascinating chemistry and physics that make portable power possible.
So at its core, a battery, it's basically a storage tank. But it doesn't store electricity directly. It stores energy in the form of chemical energy. When we hook it up to a load, which, is just a fancy physics term for any component that needs electricity to work, like a lamp, a tiny motor, or an LED, that chemical energy is instantly converted into electrical energy. You can kind of think of the battery as the engine that provides the vital pushing force. It pushes electrons through a circuit to actually do the work of, say, illuminating that lamp. Here is our lesson plan for today's explainer. 1. The basics of battery power. 2. Flow, electrons versus current. 3. Inside the alkaline battery. 4. Connecting, series versus parallel. And 5. Lab skills, testing battery voltage.
Jumping right into Section 1. The basics of battery power. The pushing force.
To understand the basic physics of how electricity moves from our power source to our devices, we really have to look at the type of current we're generating. Batteries produce DC electricity, or direct current, and this brilliantly illustrates the concept. Electrons in a DC system flow in just one single direction, from the negative side to the positive side. It's very much like a river flowing steadily downstream. On the flip side, the power outlets in your home provide AC, or alternating current. In an AC system, the electrons continuously flow forwards and then backwards. They behave much more like the shifting ocean tide coming in and going out. But for our battery circuits today, we are strictly dealing with that steady, river-like direct current.
Moving on to Section 2. Flow, electrons versus current. Which way do they actually go?
Before we look at the chemistry, we've got to address this historical quirk in physics that trips up almost every single student. If you've ever looked at older textbooks or wiring diagrams, you might have seen arrows pointing from the positive terminal of a battery to the negative terminal. That is called conventional current. It was the original theory of how electricity worked, and honestly, it's still widely taught and used in engineering today. However, we now know that actual electron flow, what is physically happening at the atomic level, is the exact opposite. Because electrons are negatively charged, they actually flow from the negative terminal of the battery toward the positive terminal. It is absolutely crucial to be aware of this distinction when you're studying circuit diagrams.
All right, Section 3. Inside the alkaline battery. Chemical reactions.
Okay, time to mentally put on our safety goggles and peel back the layers of our battery to see the intricate chemistry safely hidden inside. First up, let's look at the outer safety layers. When you pick up a typical 1.5-volt alkaline battery, you're holding a really carefully engineered capsule. On the very outside is a tight plastic wrapper. Now, this doesn't just look nice, it physically insulates the battery and tells us crucial info like voltage and polarity. Underneath that is a steel casing with nickel plating. Think of this as a vault. It holds the internal components tightly in place while stopping stuff like air and water from getting in. Finally, and this is super important, the top is sealed with a nylon plastic cap. This cap electrically isolates the positive and negative terminals. If they touched, well, electrons would flow directly through the casing, completely short-circuiting the battery. Taking a look deeper inside that casing, we find three main active layers. First is the cathode, which is connected to the positive terminal. It's made of manganese oxide mixed with graphite, which helps increase conductivity. Next is the separator. This is a highly porous fibrous paper barrier that prevents the anode and cathode materials from touching. It is soaked in an alkaline liquid electrolyte made of potassium hydroxide. And by the way, that is exactly why we call these alkaline batteries. On the other side of that barrier is the anode, connected to the negative terminal. This is a paste made from zinc powder suspended in a gelling agent. Using a powder is clever because it increases the surface area, which dramatically lowers internal resistance and vastly improves electron transfer. So what happens when all these packed materials interact? A chemical reaction kicks off. A hydroxide ion from the electrolyte joins with a zinc atom in the anode in a process called oxidation. This releases free electrons that collect on a brass pin at the negative terminal. Simultaneously, over at the cathode, a reduction reaction occurs, using water and manganese oxide. The big takeaway here is that because electrons naturally repel each other, this massive buildup of electrons at the negative terminal creates electrical pressure. And that pressure is exactly what we measure as voltage. Because the physical separator blocks them from just moving straight across inside the battery, these trapped electrons are forced to wait until we give them an external path, like a copper wire, so they can finally rush through our circuit to reach the positive terminal.
Let's move to and see how this builds in Section 4. Connecting, series versus parallel, combining batteries.
When we need more power than a single battery can provide, we usually connect them in either series or parallel. Let's consider two standard 1.5-volt batteries, each with a capacity of 1200 mAh. When we wire them in series, meaning end-to-end, positive to negative, each battery boosts the electrons as they pass through, so the voltage pushes harder, doubling our total voltage to 3.0 volts. But notice our capacity stays right at 1200. Conversely, if we wire them in parallel, connecting all the positives together and all the negatives together, the voltage stays at 1.5 volts. However, the paths merge at the supply, meaning we essentially double our pool of available energy, bringing our total capacity to 2400 mAh. Basically, one boosts the pushing force while the other extends the lifespan.
And that brings us to Section 5, Lab Skills, Testing Battery Voltage. Is your battery dead? Stepping into the practical lab portion of this explainer, how do we estimate the lifespan of these batteries? If you want to estimate how long a battery will power a specific circuit, you use this pretty straightforward formula. Battery life equals the capacity in milliamp hours divided by the circuit current in milliamps. So if you've got a 3000 milliamp hour battery and your device demands 19 milliamps, you divide 3000 by 19, giving you roughly 158 hours. But beware class, this is only a theoretical best-case scenario. In the real world, chemical reactions naturally slow down as the battery empties, and external factors like age and temperature will heavily impact performance. Because we can't perfectly predict lifespan, the only true way to know a battery's status is to test it. But here's a major lab safety and accuracy tip for you. Testing a bare battery with a multimeter might deceptively read 1.5 volts, even if the battery is practically dead and useless. To get a true reading, you absolutely must test it under a load. You'll select the DC function, then connect a resistor, around 100 ohms works great, right between your test probes. This simulates an actual device drawing power. Then, connect your red lead to the positive terminal, the black to the negative, and watch what the voltage does. Now, what's really interesting about this slide is how dramatically a truly dead battery reveals itself under these load conditions. A healthy battery might start at 1.593 volts and only dip slightly to 1.547 volts when the resistor is applied. It's holding strong. But a dead battery, it might miraculously read 1.5 volts while resting, but the second you apply that load, the voltage plummets completely, dropping way down to something like 0.863 volts. It has literally no pushing force left. And remember, when you find these completely depleted batteries, standard household alkalines cannot be recharged. The chemical reaction is permanently spent, so please make sure to dispose of them responsibly by dropping them at a local battery recycling center. So the next time you pick up a seemingly simple alkaline battery, remember the intricate engineering, the brilliant safety layers, and the massive scale of oxidation and reduction happening right inside. It leaves us with a fascinating thought. As you look around your home or even just in your pocket, how many invisible chemical reactions are silently powering your world right this second? Thank you so much for joining me for this explainer. Class dismissed. Keep asking questions, and I'll see you next time.